Hi, everyone. Remember last time when we solved the birthday problem, we had to multiply a lot of things. We had to multiply 365 times 365 times 365 many times, like 60 or more. Why do we do that? When do we need to multiply? And when do we need to add when we solve such problems? This actually is a common question from the students and a common source of confusion. When do you multiply and when do we add? Let's find out. Consider a simple example. Suppose there are 3 different flights from San Diego to Los Angeles, and there are 4 different flights from Los Angeles to San Francisco. You would like to get from San Diego to San Francisco. How many ways are there to do that? How many itineraries are there to get from San Diego to San Francisco? Obviously, there are 3 times 4, which is 12, different itineraries for you to go from San Diego to San Francisco. Here we multiplied. The reason is that for every single itinerary, for every single flight, San Diego to Los Angeles, you can take 4 different flights from Los Angeles to San Francisco, and that's why we multiply. Generally, this principle of multiplication is known as multiplication principle. Let's state it in a very general form. Suppose we perform 2 experiments. In the example above, the experiments are choosing a flight from San Diego to Los Angeles, and then choosing the flight from Los Angeles to San Francisco. Suppose experiment 1 can result in any, and this is a number of, the notation for any of m possible outcomes. In the example above, m is 3. And experiment 2 can result in any of n possible outcomes. In the example above, n is 4. Then together, there are m times n possible outcomes of this experiment combined, of the pair of experiment 1 and experiment 2. So if you need, for example, to first do experiment 1 and then experiment 2, then all possible ways to do that is m times n, and that's a multiplication principle. Here we multiply m and n. To see this, why we multiply, maybe a visual aid would be nice. If we look at the experiment 1 like this, it has m possible outcomes, and put this in the table. Experiment 2 has n possible outcomes. Then this experiment combined, if we just put all the list of possible ways how the 2 experiments can end up, all their possible outcomes is 1, 1, 1, 2, 1, 3, and so on and so forth, 1, n, or maybe the first experiment ended up in 2, 2, 1, 2, 2, and so on, 2, n, etc., m1, etc., m, n. This table is a list of all possible outcomes of the pair of the experiment 1, experiment 2. And as we can see, the number of entries in this list is m times n. And so that's why the multiplication principle works and gives us m times n here. more generally, if we have more than 2 experiments, maybe k experiments, if experiment 1 can result in n1 outcomes, and experiment 2 can result in n2 outcomes, and etc., and experiment k can result in n sub k outcomes, then collectively all these experiments together can result in this many outcomes. It will become clear from the next example what we mean by more general situation. Here's an example. How many 4-letter words are there? With meaning or without? Without any meaning, possibly. 4-letter words such as, for example, tint is a word. This word does have a meaning, but we look at all possible combination of 4 words. How many? Well, there are 26 ways to choose letter 1, 26 ways to choose letter 2, 26 ways to choose letter 3, and 26 ways to choose letter 4. And we multiply this by the multiplication principle. If we think of experiment 1 as choosing letter 1, that can be done in one of the 26 ways. For each selection of letter 1, there are 26 selections, possible selections of letter 2, and so on and so forth. And that's why we multiply that. And the answer is 26 to the power of 4, which is, I put it in the calculator, and the result is 456,976 possible 4-letter words. Got it? Okay, next example, slightly more advanced. How many 4-letter words are there, again, with or without meaning, but the words that consist of all different letters? In the previous example, for instance, the letter T was repeated, and let's not allow it now. We require that all 4 letters be different. So tint will not work. But for example, mint would work. All the 4 letters are different here. All right, let's think. Let's look at this as 4 experiments that we do in a sequence. The first experiment is to choose the first word, and that can be done in how many ways? 26 ways. That's how many letters there are. The second letter, this is a trick. The second letter can be potentially done in 26 ways, but we disallow the first letter, right? We cannot repeat the first one. So there is only 25 possible selections for the second letter. For the third letter, we cannot repeat the first 2, and that leaves us with 23 possible selections, 24 possible selections, sorry, for the third letter. And then the 4th letter cannot repeat any of the first 3 already chosen. And that leaves us with the 23 letters. So this is a number, which is 358,800. This is the number of all 4-letter words, with or without meaning, but that consist of all different letters. Another example. This one will be repeated many, many times in the probability course. If we flip a coin, let's say 5 times, what is the number of all possible outcomes? And by an outcome, I just mean what face the coin will come up. For instance, it could be head and then tail, then head, and then tail again. These are the outcome of the 5 flips of the coin. Head, tail, head, tail, and any combination of this is possible. Well, the number of outcomes, obviously, well, the first flip can result in 2 outcomes, head or tail. The second flip, again, 2 outcomes, the third, the fourth, and the fifth. 5 flips. So total, it's 2 to the 5, which is 32. And one more example of a similar kind. If instead of a coin, you toss a die. Dice is a plural for a die, the word you hear most. But a die is a cube with whose faces are marked with dots from 1 to 6. It's a 6. The cube has 6 faces. You toss a die 5 times, the number of all possible outcomes. What do you think it is? It's like a coin, only 6-headed. So the first experiment can result in any of the 6 outcomes, and the second is the same, third, fourth, fifth. There are 5 tosses, and so it's 6 to the 5, which is 7,776 possible outcomes. Now we came to the first concept of the probability or combinatorics in this case, and that is permutations. Let's ask ourselves a question. Suppose we fly somewhere to a different country, to Europe maybe, and as we exit the plane, there are n passengers who exit the plane, they spontaneously form a line in front of the passport control, the border control. How many ways are there to form such a line? In how many ways can n people form a line? Here's a line. There's people, and there is a border control, like passport control. This. How many ways are there for n people to form a line? Let's solve this. Let's solve this by thinking of this as an experiment. In this experiment, our first step is to select the first person in the line, the luckiest one, who will get to the border control first. How many ways are there to do that? Well, there's n passengers, so there's n possible ways to choose the first person. Then the second step is to choose the second luckiest person, the second person in the line. Since the first person is already selected, the number of possible ways for the second person is n minus 1, excluding the first. The next step is choose the third person in the line. And because the first 2 are already selected, the possible ways to select the third person is n minus 2, excluding the first 2. And we keep going, n minus 3 times n minus 4. And by multiplication principle, we multiply all that. And the last numbers in this product will be 5, 4, 3, 2, and 1. So this is the answer. It's just the product of all numbers between 1 and n. And this number in mathematics is denoted with the exclamation mark like this, just like that, and is called n factorial, the factorial of n. This is an important concept that will play a significant role in probability, as you will see. Example: how many different words can be made of three letters. Let's take U, C, and I. Three-letter words, no repetition. The answer, well, isn't it similar to the line problem? Do you see that? Think of the letters as people, and the word as a line formed of these people. So the answer should be 3 factorial. 3 times 2 times 1, which is 6. Let's check that. We can do this by hand. It's UCI is one word. UIC, IUC, ICU, UI, and CIU. That, I think that's it. That's 1, 2, 3, 4, 5, 6. Yay, we got it. 6 different letters, 6 different words made of 3 letters, UC and I. This concept, the concept of rearranging the people in the line into a line, rearranging the letters into a word is so general that it has a name, and it's called a permutation. A permutation of n different objects, people or letters, for example, is any ordered arrangement of them, of these objects. And as we have just seen here, there are exactly n factorial different permutations. And the factorial, again, is just the product of all letters between 1 and 2. For instance, 1 factorial is just 1, and 2 factorial is 1 times 2, and 3 factorial is 1 times 2 times 3, which is 6, and so on and so forth. There is one interesting convention here. What is 0 factorial? It is not very clear how to think about 0 factorial. How many ways can the 0 people stand in line? What is this about? How many words are there of no letters at all? So the convention is that 0 factorial is set to be 1. Later, maybe 1 or 2 classes, we will understand why people would like to make that convention. It makes some formulas just simpler. For now, let's just remember that the n factorial is just the product of all numbers between 1 and n, and 0 factorial, by agreement of mathematicians, by convention, is set to be 1. To finish off, let me ask you 2 trick questions. First question, example. How many ways are there to arrange n people in a line? By the way, if I ended here, the answer will be n factorial, of course. But so that Jessica, one of these people, is always in front of Yuki, another person in this group. How many ways can people stand in a line so that Jessica is always in front of Yuki? I said it's a trick question. You should be able to solve this problem directly, and it will be quite a computation. But there is a trick how to solve this problem easily without any computation at all, just by thinking. And that trick is called the symmetry trick. Jessica, either Jessica is in front of Yuki in any arrangement, in any line, or Yuki is in front of Jessica. However the line is formed, in any of the n factorial possible ways to form a line, either one happens, Jessica in front, or the other happens, Yuki is in front. Nothing else can happen. Yes? Now, because of the symmetry, because Jessica and Yuki are just names, are just labels of the people, there are the same number of ways to place Jessica in front of Yuki as the number of ways to place Yuki in front of Jessica. The total number of arrangement is n factorial. And so what's the answer to this problem? N factorial divided by 2. Again, this is because there's n factorial divided by 2 ways to place Jessica first, and there's and the same number, of course, should be for Yuki to be first. The sum must be n factorial, and so each will be n factorial divided by 2. So this is a symmetry trick, the symmetry argument that gives the answer to this problem, n factorial over 2. Let me just finish with a question for which I will not give you the answer, but I would like you to think of it by yourself. How many ways are there to sit n people in a circle? Maybe think about a lawn and you're sitting, you would like to sit, in this case, 1, 2, 3, 4, 5, 6, 7 people in a circle like this. It's very similar to a line, except you just join the endpoints of the line. Think about this problem, try to do it by yourself, and stay with me for the next episode.